Hello everyone, welcome to my channel Keep Exploring. In today's video, we are going to discuss exercise 1.3 from the chapter Number Systems Class 9 NCERT. So let's start. The first question says write the following in decimal form and say what kind of decimal expansion each has. So the first question is 36 by 100. Now 36 by 100 is a decimal fraction. So it can be easily converted to a decimal number, that is 0.36, and it is a terminating decimal expansion as the decimal places stops at 6. For two decimal places it will go. Now moving on with the next question, 1 by 11. Now 1 by 11 is not a decimal fraction, so we need to do the division process to get the quotient and remainder. Now see here. Now when you focus on the remainder 1, so the remainder 1 repeats itself again after two places. See here. The remainder 1 again it repeats itself. So here the division quotient, whatever the quotient we get, it will keep on repeating itself. So we get the answer as 0.09 and 09 upon bar, because 09, the group of digits 09 repeats itself. So this is a non-terminating repeating decimal expansion. Non-terminating because it will never stop itself, and repeating, we can see here the number 09, the digit 09 repeats itself. The next one, 4 whole 1 by 8. Now 4 whole 1 by 8 can be written as 33 by 8. Now 33 by 8, let's do the division. So when we divide 33 by 8, we can see that we get the quotient as 4.125 and the remainder is 0. Since the remainder is 0, then we can clearly say this is a terminating decimal expansion. So from here it is clear that whenever the remainder is 0, it is a terminating decimal expansion. Moving on, the next question, 3 by 13. So again we need to divide it, 3 by 13. Now you see here the remainder 3. The remainder 3 again repeats itself. The remainder 3 again repeats itself after the first place. Now you can see here we are getting back it again as 3. So we need to continue it again. So we need to follow this same set of digits. So our answer becomes 0.230769 upon bar. So the digits 230769 repeats itself again and again. Now, so this will be called as a non-terminating repeating decimal expansion. The next question, 2 by 11, the same way, you can see here again, the remainder 2, it again repeats itself. So the digits 1 and 8 again will keep on repeating. So we get 0.18 upon bar. So this is also a non-terminating repeating decimal expansion. The next question, 329 by 400. When we do the long division, we can see here we reach the remainder as 0. So since the remainder is 0, we can say it is a terminating decimal expansion. So you can see here, so 329 by 400 can be written as 0.8225. So it is a terminating decimal expansion. The next question, you know that 1 by 7 is 0.142857 upon bar. Can you predict what the decimal expansion of 2 by 7, 3 by 7, 4 by 7, 5 by 7, 6 by 7 are without actually doing the long division? If so, how? That means we need not do the long division again to find the values of 2 by 7 and 3 by 7 and so on. So let's see how it is done. So as it is given, 1 by 7 is 0.142857 upon bar. Now to find 2 by 7, let's see. So 2 by 7 can be written as 2 times 1 by 7. So now when you replace 1 by 7 by its decimal expansion, that is 2 times 0.142857, we get the multiplication as 0.285714 upon bar. So when you process the same thing for 3 by 7, 4 by 7, 5 by 7 and 6 by 7, so on, we'll get the answer. Just you have to multiply 3, 4, 5, 6 respectively with 1 by 7, as the value of 1 by 7 has been given in the question. Now when we see the pattern here, when we get 1 by 7, it is 0.142857. Now see the value of 2 by 7. 2 by 7 is 0.285714. You can see here the decimal place repeats itself after 2. So it starts from 2. So 2857, then again 14. Similarly, when you go to 3 by 7, it starts from 4. From here only you can see here 4, 2, 8, 5, 7, then again 1. Similarly, for 4 by 7, when you multiply by 4 by 7, it repeats from 5. So if you start from here, 5, 7, and then 1, 4, 2, 8. So here we can see a pattern to be followed. Now, how does this pattern come? We can understand better when we see the long division of 1 by 7. Here we see that 1 by 7, the remainders repeats itself. It's so many stages you can see. So now when we try to find 2 by 7, just you have to see that where does the remainder comes to. After how many steps we get the remainder as 2. As you can see here, after 3 steps, we get the remainder as 2. Sorry, on the third step. So here, just you have to see that what we have the third place in the decimal part. Third place is 2. So we'll start writing from 2. So 2, then 8, 5, 7, then 1, 4. So we'll get 2, 8, 5, 7, 1, 4. Similarly, for 3 by 7, now you can see here, where is the remainder 3? The remainder 3 comes after the first step only. The remainder 3 is there after the first step. So just after the first step, that is, we'll start from 4. So 4, 2, 8, 5, 7, then again 1. So this is the way we can easily get all the values without dividing. Next, express the following in the form P by Q, where P and Q are integers and Q not equals to 0. The first question, 0.66 upon bar is there. So it is a non-terminating repeating decimal expansion. So let us take x is equals to 0.6 bar. So here x we can write as 0.666 and so on, because it is repeating. Next, here let us take it as equation 1. Now we'll multiply both sides by 10. Now when we multiply both sides by 10, what we get? So 10x becomes equals to 6.666 and so on. Because when you multiply 10, the decimal place has to move one step right side. So we get 6 points, so many 666 and so on. How many times we want, we can write it there. So this becomes our equation 2. Now when we compare equation 1 and equation 2, we can find that the decimal part, you can see here, the decimal part matches each other. They are become equal. Now we can subtract. Suppose when we subtract equation 1 from the equation 2, we get 10x minus x is equals to 6.6666 minus 0.6666. Now here, when you subtract, 9x is equals to 6, because you see here the decimal part is the same. So we need not subtract that. Only the number part we need to subtract. Only the number part. So that becomes 6 minus 0, 6. Now when you follow the shifting, so x becomes equals to 6 by 9. So 6 by 9 when simplified, we get 2 by 3. So here we can say that 0.6 bar is equals to 2 by 3. Now here we have to note that why we are multiplying only 10, why not 100, why not 1000 and so on. Because here only one digit is repeated. So that's the logic here. When if one digit is only repeated, we'll multiply by 10 both sides. As it is an equation, we need to perform the operation both the sides. Next, when to subtract? We can subtract the equations only when the decimal part is the same. Then only we can do the subtraction. So to understand it better, we'll move on to the next bit. That is 0.47 upon bar. So this can be written as 0.47777 and so on. Because here the bar is upon 7, so 7 is getting repeated. So let x equals to 0.4777. So here first we'll multiply 10 by both sides. So when you multiply 10 both sides, now here why you are multiplying 10? We need to bring our decimal point just before the repeated digits, just before the repeating digits. So first you have to see how many places are not repeated. How many places are not repeated? So here we say only 4 is there. So this is only one place. So we are multiplying by 10. So when you multiply by 10, we get 10x equals to 4.777. So here we get it as equation 2. Now, can we subtract 1 from 2? Here we cannot, because when you see here the decimal part, here in the decimal part in equation 1 we have 47777, but in equation 2 we have only 7. So we have to see that the decimal place must be same. So here how we'll get, so again we see that only one digit is repeated. Now we'll focus on the repeated place. Now here only one digit is repeated, so here we'll multiply by again 10. So when you again multiply 10 for the equation 2, so 10 into 10x becomes 100x. Now 100x becomes 10 into 4.77. The point will move just one place. So that becomes 47.777. Now that is equation 3. Now comparing the three equations, equation 2 and equation 3 have the same decimal places. Now we can perform the subtraction. Now when we subtract, we need to subtract only the number part. So here 100x minus 10x becomes 90x. So 90x equals to 43. Now when 90x equals to 43, x equals to 43 by 90. Now this cannot be further simplified. So our answer remains 43 by 90. That is 0.47 upon bar is equals to 43 by 90. This is the P by Q form. Next, 0.001. So the bar is repeated. So 001, the whole three sets of digits are repeated. So here x will be written as 0.001, 001 and so on. So 001 is repeated every time. Now here we say that, is there any place that is not repeated? We do not have anything. So we'll direct focus on the repeated place. Now here three digits are repeated. So we'll multiply it by 1000. Here three digits are repeated, so it will multiply it by 1000. So when you multiply by 1000, we get 1000x equals to, the point will move three places towards the right as we are multiplying. So that becomes 1.001. We are having so many 001, 00, so we'll use it here again. So 1.001 and 001. So that becomes our equation 2. Now can we subtract 1 from 2? Yes, we can subtract, because just focus on the decimal part. Here also 001, 001 is there. Here also we have 001 and 001 and so on. So now when we subtract, we get 1000x minus x, and just you have to subtract left with left and right to right. So here we get that 999x is equals to 1, as we are just subtracting the number part. So 1 minus 0 becomes 1. So x can be written as 1 by 999. So the value of 0.001 upon bar is equals to 1 by 999. Moving on with the next question. Express 0.9999 in the form of P by Q. Are you surprised by your answer? Let's see what is our answer. Now same process, x equals to 0.99999, and that will be our equation 1. Here as only one place is repeated, the only 9, the digit 9 is repeated, we will multiply by 10. So we get 10x equals to 9.999 and so on. Here, now can we subtract equation 1 from equation 2? Yes, because the decimal places are the same. So we can perform the subtraction. So when you subtract equation 1 from equation 2, we get 9x equals to 9, because we are only subtracting the number part. So 10x minus x is 9x, and 9 minus 0 becomes 9. So x becomes 9 by 9, that is equals to 1. So here we say that our answer is now 1. So before x is written as 0.99 and so on, now our answer has become 1. So here what is the concept? The difference between 1 and 0.9999 is 0.00001, which is very much negligible. The difference between these two numbers are very much negligible, very much thinner. Now here you can conclude that 0.999 and so on is too much nearer to 1. Hence the answer 1 can be easily justified. That is too much nearer to 1. So we can treat it as 1. The next question says, what can the maximum number of digits be in the repeating block of digits in the decimal expansion of 1 by 17? Perform the division to check your answer. So here we have to perform the division and say what can be the maximum digits in the repeating block. Let's see the division. So when you divide 1, it's a long division. So here we can see that in this place, the remainder is 1. So the remainder 1 repeats itself after how many steps we have to see. So the remainder 1 is present only at the beginning. In all the cases, there is nowhere 1. So 1 repeats itself after 16 places. After 16 places. So again, when we put 0 here, again we need to start with 0. So 17 again 0. Then it will be 17 5s are 85 and so on. So here we need to stop our division because the remainder has repeated itself. So here we can say that we finally end up with the remainder as 1 from where the digits in the question will again start repeating. Now you can see here from here. So it is again repeating 0, 5, 8823, 0, 5, 8823 to keep on repeating the whole set. So now when we count, we get 16 digits in the repeating block of the decimal expansion 1 by 17. So here the answer is 16 repeating blocks of digits is there in the decimal expansion of 1 by 17. So we have to take care of the remainders. Just you have to focus on when the remainder repeats itself. Once the remainder repeats itself, we have to stop there. No need to proceed because once the remainder repeats itself, the quotient will again repeat. The whole set of quotient will again repeat itself. So here the answer will be 16 digits of rational numbers in the form p by q, where p and q are integers with no common factors other than 1 and having terminating decimal representation. Can you guess what property q must satisfy? So for this, let us take three rational numbers. Now for first one, 3 by 25. Now let's factorize the denominator 25. So 25 can be written as 5 squared. So to get a terminating decimal expansion, we need a decimal fraction. That means the denominator must be a power of 10. So here we have a power of 5. So to get the power of 10, we need powers of 2. So what should be the powers of 2? So we can get, if 5 square is there, if you get another 2 square, then it can be easily converted to 10 square. So 5 square when you are multiplying with 2 square. So denominator is multiplied with 2 square. So we have to multiply 2 square in the numerator. That is equivalent rationals. Now we get the numerator as 12. 2 square is 4. So 3 4s are 12. And 5 squared into 2 squared becomes 10 squared. Now we get the denominator as 100. So 12 by 100 is written as 0.12. Now this is a terminating decimal expansion. So here we see that whenever we get a decimal fraction, that is easily converted to a decimal number whose expansion is terminating. Next, 1 by 8. Now 8 can be written as 2 cube. The same concept, we need powers of 10. So you are having powers of 2. So we need powers of 5 to make it powers of 10. So we have 2 cube. So we need 5 cube. So 2 cube multiplied by 5 cube, it becomes 10 cube. Now 5 cube is 125. So we get the numerator as 125 by 1000. So 125 by 1000, it is a decimal fraction. So we get terminating decimal expansions, that is 0.125. The next number, 3 by 250. So 250 when factorized, we get 2 into 5 cube. So we need to do the factorization or else you'll not going to get this. So when you perform the factorization, so 5. So here you can easily see we have 5 cube. So we need powers of 10. So here we have powers of 2 and 5. So remember, we'll get powers of 10 when both the powers, the exponents of 5 and 2 are the same. So here the exponent of 5 is 3, but here the exponent of 2 is 1. So we need more 2. So let's see. So when you are multiplying by 2 squared, so 2 squared and 2, that becomes 2 cube. So we are getting the exponent of 2 as 3. So 3 into 2 squared, 3 into 2 squared, that becomes 12. 2 squared is 4, so 3 4s are 12. And 2 cube into 5 cube, that becomes 10 cube, that is 12 by 1000. That is again a decimal fraction, so that we get 0.012. So here we see that when you focus on the denominator, the factorization of that. So 25 is factorized as 5 square, 8 is factorized as 2 cube, and 250 is factorized as 2 into 5 cube. In every case, we are getting a decimal fraction, and every time we get a terminating decimal expansion. So the condition required for the q is the prime factorization of q should have only the powers of 2 or powers of 5 or both 2 and 5. If the prime factorization is in such a way, then only we'll get a decimal terminating decimal expansion. Next, write three numbers whose decimal expansions are non-terminating, non-recurring. So we know that all the irrational numbers have non-terminating and non-recurring. Like we'll take one irrational number, root 2. So when you perform the division method for finding root 2, we see that we get 1.4142 and so on. So it will keep on going, the division. So here we see that it is a non-terminating, that it will keep on continuing, non-terminating, non-recurring. Non-recurring means doesn't repeat itself. It doesn't repeat itself. So here, if it had to repeat, it would have been repeated here itself. That is 4 1, then 4 1 again. But here what happens? 4 1, then again it comes 4 2. So it has broken the pattern. So once the pattern is broken, it is not going to repeat itself. So from here it is clear that root 2, that is 1.4142 and so on, is a non-terminating, non-recurring decimal expansion. Similarly, root 3 we have. Now all the irrational numbers we can take for non-terminating, non-recurring. So the next, without using this, we can try with some other decimal expansions like directly 2.12, So what is the concept here? Here we are just breaking a pattern. So first we are having 1 2, then 1 then again 1 So every time we proceed, we are increasing the decimal places. The pattern you see, there is nothing repeating. Here 1 after 2 we get, but here again 1 after 1 we get. Suppose you consider this as a pattern 1 but here it is again not repeated. So that is 1 So here we are breaking the pattern of the decimal places. So we'll always will get non-terminating, non-recurring decimal expansion. So we can use like this 0 1 0 0 1 0 0 0 1 and so on, 2 3 2 2 3 2 2 2 3 and so on. So in this way we get any number of irrational numbers whose decimal expansions are non-terminating and non-recurring. Next, find three different irrational numbers between the rational numbers 5 by 7 and 9 by 11. For this, we need to first find the decimal expansion of 5 by 7 and 9 by 11. So for this, you have to perform the division. So when we divide 5 by 7, so we get the remainder 5 repeats itself. The remainder 5 repeats itself. So here we get 0.71425. So again the whole set will be repeated. So 5 by 7 can be written as 0.714285 upon bar. And 9 by 11. 9 by 11, again when we see here, the remainder 9 repeats itself again. So here we get 0.818181 and so on. So 0.81 upon bar. Now we need to find three different irrational numbers between the rational numbers 5 by 7 and 9 by 11 whose decimal expansion already we have. So now we have to think of three irrational numbers between them. Now here when we compare these two decimal places, here it has two decimal places, that is 8 1, and here it has some 6 decimal places, but we will consider only two decimal places. So anything more than 7 1 will be, that is, suppose we write 0.72. Now 0.72 will be greater than this number and 0.80 will be less than this number. So we are having a wide range of numbers. So it must be greater than 0.714285 and less than 0.81. So here let's see what we can write. The first one, 0.72. This is the limitation. So it should not be 1. So 0.72. So after 7 1 we get 7 2. So we can start from 0.72, then our pattern for irrational numbers, non-terminating, non-repeating. Similarly, 0.75, that will be our starting, then 02, 002, 0002 and so on. Then 0.80, that is less than 0.81. So 0.80 will be starting, then 100, 1000 and 1 so on. And non-repeating non-recurring and non-terminating decimal pattern. We have to just keep on writing. So here the important part is finding this range. So within these two numbers, what numbers lie? So we are focusing on 0.71 and 0.81. So in between them, we are having 0.72, 0.73 up to 0.80. So anything with these numbers as the starting tab. After that, we can use the non-repeating, non-terminating pattern. Next, classify the following as rationals or irrational. The first one, root 23. Now, root 23 is a root over of a non-square number, and we know that root over a non-square number is irrational. Next, root over 225. Root 225 can be written as 15 square. It is a square number. So, our result is 15. That is a whole number. Hence, it is a rational number. Now 0.3796, it is a terminating decimal part, so it is a rational. Then 7.478478. So here we see that 478478 repeats itself. So non-terminating, repeating, non-terminating, repeating. So it is also a rational number. And the last one, 1.01001000100001. So it is non-terminating, non-repeating. Hence, it is a irrational number. So that's the last question of this exercise. Thank you.